Okay, in this video, we are going to talk about electronegativity and how that is going to come into play with determining whether something is covalent or ionic. So, when we talk about electronegativity is basically a measure that tells you how strongly one atom is going to attract the shared pair of electrons when you are in a chemical bond. So when we think about this, it is important to remember that we have our nucleus, right? And our nucleus is in the center of the atom, and it has a positive charge, right? And then we have our electrons that go into all of our shells. And our electrons have negative charges. And what we find is this positive charge attracts these negative charges. So when we are talking electronegativity, we're obviously talking about a shared pair of electrons. So I would have over here some other nucleus, my super awesome drawings, with its electrons, right? And we've got first shell, second shell, and then somewhere over here, we are sharing those electrons, right? So let's say here is my shared pair. Maybe I'll do a different color to make it stand out. So here's my shared pair of electrons. It's being shared between this atom and this atom. So when we're talking about electronegativity, it's going to describe to us how strong is the attraction for this nucleus to the shared pair. And we're going to be able to compare it to how strong is the attraction of this nucleus to the shared pair. So why this is going to matter with respect to bond type is you can think of it as all of our atoms are basically in a tug of war for electrons. If they're pulling with the same amount of force or the attraction is the same, they're going to share them evenly. If one of them has more of an attraction, it might be able to take those electrons for itself, okay? So what we find is that a higher electronegativity indicates a greater attraction for electrons. So the bigger the number is, the more that attraction is. So if you go to your periodic table, well, on that periodic table, when you look, you will see that the electronegativity number are these little numbers directly above your chemical symbols. So if I look at hydrogen, it has an electronegativity of 2.2, lithium is 1, sodium is 0.9. So the smaller the number is, the less that attraction is for the shared pair. If we go over to the other side of our table, we start to see that we get much bigger numbers, right? So we have fluorine at 4, we have chlorine at 3.2. Right? You'll notice we don't really have any numbers for these noble gases for the first 4, and that's because they don't tend to participate in bonding. We do start to have some for xenon because it does tend to do some bonding, but the other ones, we don't really have an electronegativity number in our data booklet because for what we are concerned with, they are not going to participate in bonding. So the bigger the number is, right? So fluorine being at 4 versus, I don't know, boron being at 2, that means fluorine has a greater attraction for electrons than boron does. So if boron and fluorine were sharing, they wouldn't share very well because there's a very large difference in electronegativity. Okay? So we're going to be able to use that electronegativity to help us determine what kind of bond we are going to have. So to quickly review your atoms, right, and why some of the things we're going to see happen, we can remember that atoms are mainly empty space, right? We've talked about this before. We have our tightly packed nucleus, and then we have the electrons in the shells, but electrons don't really take up much space. So the majority of our atom is actually empty space. How big an atom is basically depends on how many shells of electrons do I have. The more shells we have, if you compare it to like an onion, right, the more layers your onion has, the bigger it's going to be. We found the same is true for our atoms. So what that means is when we look at our periodic table and we look at the periods, right, so as I go from period 1 to period 2 to period 3 to period 4, our electrons are going into not valence shells, but into electron orbitals that are further and further and further, right, because we're filling valence shells that are further. So what we tend to find is that the mass of atoms as we go down the periodic table is going to get bigger because there's more electrons as we go down the period. We are filling electron shells that are further and further from the nucleus. So I don't know why I'm talking about energy level diagram of carbon. We've already done energy level diagrams. We're not really going to worry about that. So as you go across a period, the number of protons increasing, the number of electrons is also increasing, right? So this is where what you find, well, that's not the right thing. That's our Remembrance Day thing. Hold on. So what you find is as you go across a period, right? So if I go from lithium to beryllium, the size pattern here is going to be a little bit different. The reason it's going to be a little bit different is we're not filling a different shell, right? So as we went this way, down a group, we were filling a new shell, so it was getting bigger. But as we go across a period, that doesn't happen because the electrons are going into the same shell. So what you are going to find happening seems somewhat counterintuitive. So if we think of our periodic table, attempt to kind of quickly sketch something out. It's not going to be perfect, but you'll get the gist of it. I'm kind of leaving helium out just because I don't feel like doing the extra little jut out up here and hydrogen up here. So what you're going to find, so size-wise, as we go down, they are going to get bigger. So atoms get bigger. Apparently my font is also massive, so let's fix that. Okay, so the atoms are going to get bigger as you go down. So a lot of times we think that as we go across a period, that they should also get bigger because we're like, well, there's more protons, there's more electrons, so it makes sense that it's going to get bigger and there's more neutrons. But we find that that actually isn't the case, okay? What we find as we go this way across our table, if you think about it, we're still putting electrons into the same shell. So they're not going in a shell that's further away from the nucleus. But what is happening is as I go from this atom to the next one to the next one, there's more protons in the nucleus. So more protons in the nucleus means that there's a greater positive charge to attract those electrons that are in the same shell. So what we actually find is because there's a greater positive charge, there's a greater attraction for those electrons. And that orbital kind of gets sucked in a little bit. So what we find is that as we go from left to right across our periodic table, the atoms get smaller. Okay, and it's because they feel what we call less of an effective nuclear charge. So if you look some stuff up online, you'll sometimes see a little abbreviation that's like a capital Z, that'd be EFF. Okay, we don't really tend to talk about that too much in chemistry, but basically that, well, not in Chem 20, other courses you will, but not in Chem 20. This refers to our effective nuclear charge. And so what we find is that as we put more protons into the nucleus, the charge becomes greater. The greater the charge is, the greater the attraction is going to be, right? I often compare it to magnets because you guys don't really sit around playing with charged things, but we've all spent time as children playing with magnets. And usually, you know, like the bigger your magnet is, the stronger it is. Obviously, there are exceptions to that. But this kind of comes down to the same thing when we are looking at these attractions. Is the greater the charge difference is, the greater the attraction is going to be. So as I put more protons into the nucleus and those electrons aren't being placed in a further shell, they're going to get drawn in more because there's more of an effective nuclear attraction from that charge, okay? So as we go down the table, atoms get bigger. And as we go across the table, they are going to get smaller. So what that means is down here, this atom in this corner here is going to be my biggest one. And the one over here, and we're kind of ignoring hydrogen as we do this because we do that sometimes, we ignore certain things, is going to be fluorine, okay? So it doesn't mean that hydrogen isn't actually the smallest, but why we kind of tend to ignore it a little bit is hydrogen only has one proton and one electron. So it doesn't have that great of an attraction because there isn't a huge difference in charge. Whereas when you look at fluorine, there's going to be a bigger difference. So obviously hydrogen, yes, it is smaller than fluorine, but because we are trying to talk about size to be able to relate it to electronegativity, that's why we're kind of ignoring the hydrogen, because there isn't going to be that large of a difference in charge between the nucleus, okay? So why we talk about the size of an atom, it's because that is going to relate to the electronegativity of the atom, right? We've now just identified that this is the biggest, and this guy over here is the smallest. So if we go back to our periodic table, that means francium is the biggest. Have a look at its electronegativity. It's 0.7. When you start looking at all the numbers around it, that's the smallest electronegativity. So that means it has the least attraction for the shared pair of electrons. Then if we go over to fluorine, it's 4. And that's the highest electronegativity that we see. And so what we find is that the smaller our atom is, the stronger the electronegativity is. Whereas the larger the atom is, the less the electronegativity is. So when we start to relate them, we see that there's that relationship, right? So a lot of this slide talks about stuff that we talked about kind of while we were looking at the last one. So what you are going to find is the smaller your atom is, the larger the electronegativity is going to be. The reason that is the smaller your atom is, the closer that shared pair is to the nucleus. And the closer the shared pair is to the nucleus, the stronger the attraction is going to be. Whereas in the case of francium, that shared pair is really far away from my nucleus. So it's not really feeling much of an attraction to it, okay? So if we go back to our little fancy chart here, we see that there's a relationship between that, right? So if we wanted to look at it, we're going to find that over here in this top corner, we have, oh, why is this not working for me? There we go. The highest electronegativity. You're going to see that we generally abbreviate electronegativity to just En. And that down here in this corner, this is where we have the lowest electronegativity. Okay, so size and electronegativity are related to each other. So we can use those electronegativity numbers to help us predict what type of bond we are going to have. So in Science 10, we use the generalization that an ionic bond is between a metal and a nonmetal, and a covalent bond is between two nonmetals. But really, the right way to determine what type of molecule you have is to actually use your electronegativity numbers. So when we talk electronegativity and helping us determine bond type, this is kind of where we go from black and white, which is what Science 10 was, right? Like ionic, covalent, there's only these two categories and that's it. Now we're starting to get into the gray area where molecules aren't actually ionic or covalent. They're always displaying characteristics of both. And we tend to refer to this, put this in a different color, is what we call the bonding continuum. So the bonding continuum basically refers to the fact that no molecule is ionic or covalent. That's not how you spell covalent, hold on. Rather, it displays, can't type, characteristics of both. Sorry, I'm kind of writing over other writing. I try to shift that up a little bit. So what we mean by that, sometimes people look at that, they're like, I don't get what that means, is at times our molecule might behave like an ionic, and we might find that that shared pair of electrons is actually spending all its time with one atom over the other. At other times, though, it might behave more like a covalent, and we might find, you know what, those electrons tend to be shared between the two of them. So when we classify something as ionic or covalent, it's not because it's actually ionic or it's actually covalent. It's because that's what it looks like most of the time. So There are definitely some gray area ones where you're going to find, usually they tend to involve some of those metals that kind of hug your staircase, where they're not actually ionic, they're actually going to be covalent most of the time. And you'll notice sometimes that when we name them, and this is frustrating for some of you, sometimes we name them as ionics and sometimes we name them as covalents, and both are kind of deemed acceptable because one way of naming kind of goes with the black and white of this is ionic, this is covalent, and the other way of naming kind of goes with the we recognize that it could be both at the same time. Okay, so how we are going to decide what it is going to be first. So I paused for a second there. I was like, this doesn't seem right. So we're going to use our electronegativity difference to help us decide what it's going to be. Okay, so we're going to use what's called the difference in electronegativity, which we abbreviate to a delta because delta means change or difference, and then En for electronegativity. So we use that to help us decide what type of bond we're going to have. If we find that there's next to no difference in that electronegativity, right? So if we have a delta En of 0, we consider that to be a non-polar covalent bond, okay? And we consider it to be non-polar. You're going to see that we kind of have three covalents here. We have non-polar covalent, we have slightly polar covalent, and we have polar covalent. And then we get to here where we have ionic. So ionic means ionic, right? We are saying when we classify something as ionic that the majority of the time the electrons are spending their time with the nonmetal and not with the metal. Then we get into covalent. So covalent means we are sharing. The difference between polar covalent and not polar covalent is referring to how we are sharing. There's different ways you could share, right? Think about like if you and a friend were eating a cake. Maybe you're going to split it down the middle. You're going to share it perfectly evenly. But maybe you're going to take a slightly bigger piece. Or maybe your friend is going to be like, I'm really hungry. I'm eating all of this and I'm giving you a tiny little sliver, right? So you're still sharing, but you may not be sharing evenly. And so that's where nonpolar and polar covalent come into play. So when we say nonpolar covalent, that means you are sharing evenly. So when would we share evenly? Well, if we have an electronegativity difference between our two atoms that is 0, we're going to share evenly. So if you think of like H2 gas, we have two hydrogen atoms. They both have the exact same attraction for that shared pair. So they are going to share it evenly, and it's going to be a nonpolar covalent. Then we kind of get into this 0.1 to 0.5 range. Most of the time, someone's ringing my doorbell. My dog's going to start barking. Oh, maybe not. It says slightly polar covalent. Most of the time, we still consider it to be non-polar covalent because we are sharing still relatively evenly as far as that goes. Okay, so ignore all this. Let me erase that for a second. So then we get to an electronegativity of 0.5 to 1.6. So when we were dealing with 0.5 to 1.6, and sorry, I think you need to change that in your notes. It might say 1.7. We consider this to be polar covalent. So when we say something's polar covalent, we're not sharing evenly anymore. Still sharing, but not sharing evenly. They're going to be spending more time with whichever atom has the higher electronegativity. Then we get to an electronegativity difference of 1.7 to 3.3, and we are going to consider that to be ionic because what's happening is we are sharing those electrons so unevenly that we consider them to basically be transferred over to the non-metal. So technically, everything displays characteristics of both ionic and covalent bonds. However, we use electronegativity differences to still allow for us to try to classify things so that we can make sure that we treat them correctly and we do the right types of diagrams. So anything between 0 and 1.6 is considered covalent. We are sharing electrons. How evenly we're sharing them, that's going to depend on the electronegativity difference. We're going to be able to classify the bond as either being a polar covalent or non-polar covalent. When we say non-polar, That means there's no electronegativity difference, we are sharing evenly. When we say it's polar, that means we're sharing, but we're not sharing them evenly. And we tend to say polar because we're referring to two poles, where you're going to see as we move further along that one is positive and one is negative. And then obviously we hit that 1.7, which is kind of the cutoff number, and anything that's 1.7 or greater, we are going to consider it to be ionic. So we can use this electronegativity difference to help us determine how those electrons are being shared. So when we go back to this particular question, or not question, slide. So what we find is that we kind of change our definition. So what we should really be looking at is that electronegativity difference. So if we look at CH3Cl, right, if we were to go about drawing that, and of course I haven't really left myself much room to actually draw this, we would have our carbon in the middle because it has the most unpaired. We would have a hydrogen up here, a hydrogen over here, and another hydrogen, and then we would have our chlorine. Okay, so you're going to find most of the time when we are talking electronegativities and bringing them into our diagrams, we're usually looking at either structural or you're going to see VSEPR diagrams in the next lesson, or maybe it's 2 lessons from now. We're going to look at our structural diagram. So when I'm trying to figure this molecule out, generally we're going to look at the bonds themselves. So I'm going to look at a carbon to a hydrogen bond, and then I'm going to look at a carbon to chlorine. I don't need to look at carbon to hydrogen again because I've already done it. So electronegativity wise, right, if we're looking at a carbon to a hydrogen bond, we go over to our periodic table. So carbon is 2.6 and hydrogen is what, 2.2. So the difference between 2.6 and 2.2 is 0.4, right? So what we're going to wind up with is, because it's 0.4, this is going to be considered a covalent bond. We are sharing. We're sharing relatively even because we're only at 0.4, but we're still going to find that our electrons are going to spend just a little bit more time with the carbon than they will with the hydrogen, right? Our electrons that are in this shared pair are going to kind of be drawn in towards the carbon. And the same is going to be true here and here. And that's happening because the carbon has the higher electronegativity between the carbon and the hydrogen. So that shared pair of electrons spending a little more time here. And this shared pair spending a little more time here. This shared pair also spending a little more time here. When we compare the carbon and the chlorine, because that's our other bond, we have to get the difference between 3.2 and 2.6. And so that is 0.6. So again, it's still going to be covalent, but now we're getting into that polar covalent stage, which we kind of had with the other ones, but they were only slightly. This one's a little more. So because the chlorine is higher, those electrons that are in this shared pair are going to be attracted over towards the chlorine. So what we wind up with is a bunch of these little partial charges. So we use partial charge symbols, which are indicated by this lowercase delta positive and delta negative to indicate the partial charges that are present, okay? So how these are going to come into play is, think about electrons. Electrons have negative charges. If my electron, if this shared pair is spending a little bit more time with the chlorine than it is with the carbon, then that means this chlorine has that partial negative charge because those electrons are being drawn this way, right? When we look at the hydrogens, their electrons are being drawn towards the carbon, so those electrons are spending less time with them. So they're going to have a little bit of a partial positive for each one of them because all of their electrons that they are sharing are being attracted a little more so towards that carbon. Okay, our carbon's a little wonkier because with respect to the hydrogen, sorry, I put negatives and those should be positives. So the carbon's going to be a little bit wonkier because with respect to the hydrogens, it does have that partial negative. But with respect to the chlorine, it has a partial positive. Okay, this is why generally when we are looking at electronegativity differences, you'll see when we get to molecular polarity, we're going to look at the whole image. But a lot of the times at this stage, when we are talking about whether a molecule or a bond, sorry, I should say, is going to be polar or ionic, we're usually just talking about one atom to another one so that we don't wind up in this position where carbon is kind of both, okay? So if you are asked to show the electronegativities and to show how they are going to impact those individual bonds, you should be using the arrows as well as the little partial positives and partial negatives. All right, let's see if there's another example at the bottom of that page. Not really. But yeah, so as you start to work through it, I mean, you do have the carbon to chlorine here. We already did kind of look at that when we did our bigger one there, right? We know the chlorine was what, 3.2 and carbon was 2.6. So electrons are going to be drawn towards the chlorine. Because electrons are going there, it's going to have a partial negative, and the carbon is going to have a partial positive. So things to get out of this. Nothing is actually ionic or covalent. Everything displays characteristics of both due to the bonding continuum. We are still, however, going to use those electronegativity differences to classify them so that we can make sure we do the appropriate types of diagrams. We need to be able to recognize how electronegativity is going to impact that individual bond polarity, right? And this is referring to bond polarity. Because the shared pair of electrons is attracted towards the chlorine, it has a little bit of a negative charge, and the carbon winds up with a little bit of a positive charge. This is going to matter as we move forward in the unit because we're going to use those individual bond polarities to help us determine the molecular polarity. Okay, so practice-wise, I want to say there is a worksheet in your booklet, probably called Electronegativity. It's going to have you doing some of these, also have you classifying things as either being ionic, polar covalent, or non-polar covalent. So if I decided that my molecule was non-polar covalent, because I didn't do an example of that, right? If I had, I don't know, H2, I wouldn't change anything about my diagram. It would just look like this, right? It would be a structural diagram. There would be no partial positives or no partial negatives because they both have the same attraction for the electron. There would be no arrow because that shared pair is going to be shared between the two of them, okay?